Today we learn topology. Topology is an interesting subject in pure mathematics. And topology comes from study of real line, Euclidean space, and study of continuous function on this space. Now we discuss about set first. Set is a well-defined collection of distinct objects. Set denoted by capital letters X, Y, Z, and set is a collection of distinct objects. Which collection must be well defined. That means we construct a set 1, 2, 3 as elements of this set X. Then these sets contain 3 elements, and again we construct Y, A, B. These sets contains 2 elements. Again we construct Z, small x. Then Z contains 1 element. And also we familiar with more sets, Z plus, Z, Q, R, C. That means Z plus set of positive integers, Z set of integers, Q set of rational numbers, R set of real numbers, C set of complex numbers. So what we know now? We know set. Set is a collection of distinct objects. Distinct means we construct a x1, 1, 2, 1, 3. Then these sets are not well defined because here 2 elements are same. So where we write it, how we write it, 1, 2, 3 is better representation of this x1. So we construct and understand basic definition and some common example of set. Now further proceed. A set of collection. That means collection of sets. We construct collection of sets tau. Tau is a collection of sets denoted by tau, where phi, singleton 1, singleton 2. Singleton 1 is a set contains 1 element, singleton 2 is a set contains 1 element, and phi is empty set. Phi empty set. Singleton 1 is a set contain 1 element. Singleton 2 is a set contain 1 element. And tau is a set which contain 3 sets. That means tau is a collection of set. Now we define collection of set. How we define collection of set? We define it more appropriately. Collection of set means a set contain some collection of sets. That means a collection of set is a set which contain sets as element of this set. Now we define a topology. A topology play an important role in pure mathematics. A topology defined on a set. A topology on a set X, defined on a set X, is a collection of subsets of X which satisfies some basic properties. Those are: first one, phi empty set X whole set belongs to this tau. Her tau is collection. Number 2, if AI belongs to tau, then arbitrary union I equal to 1 to plus infinity AI belongs to this tau. And finite intersection, if AI belongs to this tau, then intersection of I equal to 1 to n AI belongs to tau. Then tau is called a topology. So we discuss some familiar example, and this tau is called topology, and X tau is called topological space. X is set and tau is topology. X tau is called topological space. Now we discuss with some familiar example and well-known example. First we start taking a collection tau 1 where phi empty set belongs, X whole set belong, singleton 1 belong. So where X I take two element set 1 and 2. Now we discuss which one is topology or not. We check it first. First we see that phi X belongs to tau 1. We see it. Next, phi union X equal to X. Phi union singleton 1 equal to singleton 1. and x union singleton 1 equal to single x. So all unions of two sets from these collections are obviously belongs to this collection tau 1. Now we union of three sets phi x and 1 obviously x, and this must belongs to tau 1. So we taking union of those sets from this collection, and obviously those are belongs to tau 1. So tau 1 satisfies second properties of the definition. Next, phi intersection x equal to phi intersection singleton 1 equal to phi x intersection singleton 1 equal to singleton 1, and phi intersection x intersection singleton 1 equal to phi, all are belong to this collection. So tau 1 be a topology, and x tau 1 be a topological space. Now we discussed one more example which is so simple. We first talk about simple example because simple example understand the topics. The first known topology, so we start from simple example. Now we construct one example which we check this set of collection. We check this set of collection is topology or not. We start phi x 1 2 where x is 1 2 3. We take a collection phi empty set x whole set 1 singleton 2 in tau, where x is a set which contains 3 elements 1 2 and 3. Now we check it, this one is topology or not. Check tau 2 is topology or not. First we see that or we observe that. Which one we observe? Phi and x belongs to tau 2. But one thing is, something is problem here. What problem? We take one singleton 1 union singleton 2. Then these two unions are sing 1 and 2, but does not belongs to in tau 2. So this one is topology or not? Not, because this does not satisfy second condition or arbitrary union condition of this topology. So tau 2 is not a topology. Now further construct some example to understand topology. Which example we start? We start a 3 element contain set, and then we construct some topology from these 3 elements. And how much topology is from, I'm not tell all of them, but I'm construct one 3 element set ABC. Then we construct some collection which from topology. That means first tau 0 phi x. This one we call a indiscrete topology. Indiscrete topology. And tau collection of all subsets. That means power set of x. Which one? Phi x, singleton A, singleton B, singleton C, single AB, BC, CA. This collections also from a topology. This one called discrete topology. And we further check it in our home and also find 29 topologies from this 3 element set. That means we construct our one also phi x a, tau 2 phi x b, tau 3 phi x c. That means 3 type of this one. Now we further proceed, then more and more. Total 29 topologies come from these sets. I'm not discuss about this now, but further you know about it. Next we are discuss some finite complement topology. This is very interesting topology. Finite complement topology. We denote it by tau f. Topology is the collection of all subsets U of X. Topology contains all subset U of X such that which property follows? Properties are X difference U either finite or is all of X. Either finite or all of X. That means complement of U in X must be finite. That means complement of U in X contains finite elements. Otherwise, phi also belongs to this. So, we first see that phi must belongs to this one. Because phi, I take it x minus x, x difference x equal to phi belongs to tau f. And obviously x difference phi not needed this one now, because all of x either finite or all of x. That means x difference phi is x belongs to tau f. So we find phi and x belongs to tau f. Now we take U alpha belongs to tau f, then we have to show that if U alpha belongs to tau f, we have to show that union of U alpha belongs to tau f. We further proceed x minus union of U alpha equal to, that means x difference union of U alpha equal to intersection of x difference U alpha. And we know from this definition of these sets x minus U alpha, if U alpha belongs to tau f, then x minus U alpha must be finite and intersection of finite set must be finite. So this belongs to tau f. Again we construct x minus x difference finite intersections of ui equal to finite union of x difference ui. This obviously belongs to tau f because x minus ui are finite and finite union of finite sets must be finite. So tau f become a topology. Now we discuss co-finite topology. In this way, in same manner, we also discuss co-countable topology or countable complement topology. Countable complement topology defined in a same manner, denoted by tau c. Denoted by tau c, where all u subset of x such that x difference u either countable or is all of x. This also satisfies three properties of topology in same manner. So countable complement topology we call it countable complement topology because tau c is a topology also and satisfies three properties of this topology. Definition of this topology. Now we further proceed some finer and strictly finer and coarser and strictly coarser. That means how we compare these two topology. How we compare these two topology. How we compare these two topology. Topology is a collection of subsets of a set. Topology is a set. Topology on a set is a collection of subsets of this set. Now we consider two topology, tau and tau dash. Then these two topology, obviously these two topology on a set X, and these two topology tau dash is finer than tau. If tau dash properly, if tau dash contain tau, properly contain tau. Some basic example, we construct tau dash phi x1 2 and tau phi x1. Then obviously tau dash is finer than tau. And also this one is strictly finer because contain properly, then tau dash is strictly finer than tau. Same thing we now write it. Tau is coarser than tau dash, and obviously here this example, from this example, tau is strictly coarser. Okay, tau dash is finer than tau or strictly finer here in this example, and also tau is strictly coarser than tau dash. That means we compare these two topology, tau and tau dash. Tau is comparable with tau dash, is either finer or coarser. Okay, then I think we understand the basic definition of topology and some concept of topology, and familiar with some basic example. We start from it and further proceed, then we understand topology properly, and this plays important role in pure mathematics. So from beginning we understand topology more better way. Bye.